Okay, good morning. Welcome back to Calc 2. So here we are. We're going to be talking about three-dimensional maximums and minimums. Okay, two-dimensional maximums and minimums. So a little bit of review from Calc 1. Okay, you recall that when you took the derivative, right, you'd have, if I wanted to find a maximum or a minimum, we would take the derivative of a function, right? Get f prime, set it equal to 0. So first take the derivative, set it equal to 0. 2, solve for x. And then 3, generate the x's where f of x equals 0. Okay, so we find x such that f prime of x equals 0. At that point, we would say, oh, that's a critical point, and we could test to see if it's a maximum or a minimum. So we could look at the behavior of the graph. If before that point we had the graph, we had the first derivative negative and then positive, we'd say, oh, it's negative and then positive. So this must be a minimum, or opposite, we'd have a positive and then a negative. So we go up, peak, and then go down. So we'd have first derivative, right, greater than 0, and then first derivative less than 0. So we'd say, oh, it must have gone up and then come down, so we have a maximum. Okay. We can't do that easy thing. Oh, there we go. Okay. So we can't do this easy thing in in three-dimensional, because while one direction might be going up, you might be dealing with a different direction going down. So you can't just say first derivative set equal to 0 and solve, and then like look at the geometry and see what's happening. I mean, that's exactly what we're going to do, but it's got to be more complicated than just, is it up or down, or is it down and up? Okay, so we'll go with that. You might remember that there was something called the second derivative test, right? In which case we were looking to see, well, is it positive or negative? What's going on with that? And that's how we're going to go through and deal with this, okay? So in 2 dimensions, 3 dimensions, right, we actually have to track what's going on with the second derivative of x, but we also have to track the second derivative of y. And then because there's interaction between them, we actually have to get both of them together, okay? So there is a formula that we use, okay, and that's the second partial of x, right? So we have d squared dx squared, okay? And we're going to use this formula for almost everything that we're going to do, okay? So this is dy squared, or sorry, dy squared. But there's an easy way to remember this thing, but first off, unless you're working with it on a regular basis, you generally have to look this up, which is fine. And secondly, it really helps if you were exposed to matrices before and you weren't. So we're going to just know this formula. I will provide this formula to you, okay? So we are not going to have to memorize it. This is something that we'll have time to look up. So what we're going to do is we're just going to say, okay, derivative of actually, this has got to be squared. Okay. We're going to take our critical point, AB, or our list of critical points, okay? Take the second derivative with respect to x, take the second derivative with respect to y, take the cross derivatives, plug in your AB, plug in your AB, and that's going to be, we call that a D equals this, okay? And this comes from the matrix because this is the determinant, okay, for this matrix. That's why it's called D, and that's what we're going to inspect here, okay? Now, even if I remember this formula, sometimes I do, but then we've got to consult a little chart, okay? And there's a chart right here, okay? So if your second derivative of x is less than 0, right, it's negative, and d is positive, then we're going to get this information. When the derivative, when this determinant equals 0, we're going to have an issue, and it could be a saddle point, okay? Which means we have to do something else, okay? Why is a saddle point? So we don't have to do anything else. That just means that that literally means that on one axis right? We're here, and on the other axis, we are there. So it is both a min and a max, depending on which direction you're looking at, okay? If it's no information, then we have to use other methods, but you don't have that opportunity, okay? We don't have other methods. This is it. Fortunately, I do not believe that there are any problems that, well, there's one or two homework problems that actually do have a 0 here, but the geometry for them is pretty easy to deal with, so you can tell, okay? So you're going to have, so if you're doing your homework and you've got this chart printed out right here, okay, that's exactly where you need to be, because you are going to be provided this chart, okay? So we're not going to be dealing with, like, you have to know this. Like, no, you don't. It's provided, okay? So on our quiz, it's going to be number 5, okay? So you have access to it, because I'm not sure how I can put a file in there and not have this done and then have it cluttered. So you're just going to have access to this chart the entire time, okay? So again, problem 5 has a chart. So yeah, let's just get going. Part of it is kind of difficult because there's a lot of algebra involved, and my intermediate algebra class right now is solving these kinds of systems, and that's what they're doing, and they are having difficulty with them, and I know you guys are having difficulty with them. They're not the easiest problems sometimes, okay? So I know we got to practice a little bit, but we're kind of stuck with what's going on there. All right, so let's have a look at what we're doing for homework here. Let's see if we can't have a look-see. So this is 9.3. 9.4, that's not there on purpose, okay? We used to teach that in the class, and we decided that, well, I already know, like, those are problems that are a lot more difficult than everything we're going to meet in this section. Okay, so let's go ahead and have a look-see and see if we can find a nice one. Okay, perfectly good. Most of your problems are actually going to look like this. Okay, it's a x squared plus some kind of a y squared. There's usually a mixed term, and then there's a linear couple of terms here. Okay, so this is the majority of what the kinds of things in your homework ask you to do. Okay, is this guy right here? I can do this, I think, a little bit. Make it a little bit bigger, but there we are. All right, so why don't we just take a look at it? Okay, we've got 2x squared plus 3xy plus 4y squared minus 5x minus 2y. Here's your strategy. We have to find partial of x, okay, and set that equal to 0. We have to find partial of y and set that equal to 0. These are going to give us our critical points. Okay, we're still going to have x's and y's. We're going to have 2 equations with x's and y's set equal to 0. We're going to solve them. We're going to see what happens. Okay, we might use one equation here to substitute or to eliminate an equation over there, but that's how we're going to get our critical points. Okay. Then we're going to test the critical points. We're going to take second derivatives of everybody, okay, and f, y, y. We're going to plug in the critical points that we found, a, b, a, b, a, b. If you can. So a lot of times it's just going to be a constant. You can't do it, okay? And then we're going to go ahead and, again, this is going to be written down for you. We're going to test fxx times fyy minus fxy, or yx, doesn't matter, squared at those points, and see what happens here. Consult the oracle and get our answer. Okay, so that's the strategy. Take first derivatives of everybody. Your calculus teacher, Calc 1, probably did not impress upon you doing second derivative test. I don't, okay, because there's easier ways to get this, the max or min rather than second derivative test. But now we're stuck with second derivative test. All right, so that's what we're going to do. So my fxy is equal to 2x squared plus 3xy plus 4y squared plus 5x minus 2y. All right, take our first partial. All right, so Remember the x, right? So that's 4x. We have plus, remember the y is considered a constant. So this is 3y, okay? Y is considered a constant. So this term only has y's in it. So this is all constant. Okay, so my partial is 0. Okay, here we have plus 5 because derivative of x is just going to be 5. And we're going to set this equal to 0. Okay, it's a semicolon. Okay, then we have df dy, and we're going to do the same thing. So here, right, we have constant, and then we have 3x, because y is a constant, 2 times 4, that's going to be 8y, okay? This piece is a constant because it's derivative of y. X doesn't contribute anything here. Minus 2 equals 0, okay? So you can see we have two equations, two unknowns. We're going to solve these against each other, okay? But while we're in a calculus mood, why don't we just finish taking derivatives? Okay, and we'll collect what we need to collect in a moment. So I'm going to take the second derivative of x, okay, with respect to all of this. We're just taking derivative of x. So this point here, 3y, that's a constant. 5 is a constant. 4. It's the only thing we have to deal with. 4. Okay, d squared f to dy. Okay, second derivative of y. This is going to be constant. We have 8. 2 is a constant. We're done. Okay, and then finally d squared f, and then we have dx dy. So it doesn't matter, right? Technically, these are not going to be equivalent if you swap them, but every problem in this book you can swap, it will be the same. Okay, so just want to mention that it's not always going to be the same, but for every problem you're going to meet in this book and every problem you're going to meet in an engineering class, you're going to be able to swap them. Okay. So taking the derivative here with respect to y, so 0, 3, 0, and 0. Okay, so in this case, like, well, what about a and b? Well, a and b doesn't matter. We have the second derivatives regardless, and we're going to be able to calculate that d score, the discriminator score, with no problem, even without knowing what a and b are. Okay, so at this point, you could do them in any order you want because these don't have x's and y's to plug in. Okay, but we'll do it in the order that I said. So we have 4x plus 3y equals minus 5. That's from this equation here. All I did was sweep the minus 5 to the other side. And then on the other side, the other problem here, we have 3x plus 8y. Oh, no, I'm sorry. That's yeah, that's right. 3x plus 8y. And again, I'm just going to sweep this 2 off to the other side. We've got this. Okay. Now, this is a system of equations. I know that you've all seen this in either high school algebra or in intermediate algebra. Okay. And unfortunately, we don't reinforce this in college algebra, so it's probably the last time you saw it. You have options. Okay. This is a systems of equations. If you find, if you go and say systems of equations worksheet, you'll have dozens more problems. If you have a spare intermediate algebra, even a high school algebra textbook laying around, okay, it's going to be under systems of equations. You're going to give you a choice. They're going to say elimination or substitution. Even in my intermediate algebra class where they actually break these down into 2 different chapters, like I tell them, I don't care which one you use your favorite. Okay, my favorite is usually elimination because that's an easier way for me to think about things, but if you like substitution, you go right ahead and use substitution. Okay, so what I'm going to do to solve these 2 equations is I'm going to each multiply them by something different, and the goal is to find something that's going to make these 2 equivalent but opposite signs, or something that makes the y's equivalent but opposite signs. We don't care about the y's and x's. So what I'm going to do here is I'm going to multiply by -3. I'm going to multiply this one by 4. All right. So 4 times -3, that's going to be 12, -12. 3 times 4 is also going to be 12. They're going to eliminate. Okay, so we've got minus 12x minus 9y equals 15. Okay, the biggest mistake students make on this problem is they forget the right-hand side here. They get so excited, like, yay, I solved it. And then like, well, what about this part? Oops. So that's the mistake that most people make right there. So here we've got 12x, and you know, for the people who like you're too cool for school or something, I don't know. But and I'm not saying that to be like offensive or anything like that. You know, people can take shortcuts. You're old enough to do that. But when you're doing this and you're making some mistakes, please slow down, take each step one at a time and go through it this way, because there is a lot of mistakes that you can make doing these problems. Okay, so negative 12 and positive 12, that's 0. We don't have to write that down. Okay, and then we've got 32 minus 9, so that's going to be 22. That's going to be 23. 23y here. Okay, 32 minus 9, and then 15 plus 8. Hey, what do you know? That's happens to be 23. I had no idea that was going to happen, but that's what we have. So at the end, right, it's a semicolon. So I'm just going to divide both sides by 23. 23y equals 23. Divide both sides by 23. And we get y is equal to 1. Okay. So once we know y is equal to 1, you can pick any equation you'd like to up until the end here and get the value for your x. So we could say this is 4x. Okay, I'm just picking this first equation right here. Plus 3 times 1 plus 3 times 1 is equal to minus 5. Okay, so we have 4x plus 3. So what I'm going to do is I'm going to subtract 3 from both sides. And we get 4x equals minus 8. X is equal to minus 2. Okay, so my critical point, negative 2, 1. Okay, so critical point, negative 2, 1. Right. Just notice, like, so just thinking about how I have to grade this. How many mistakes could we have made up until now? Okay, so I'm not looking for perfection when we're doing this. I'm looking for like strategy and overall, like, what are you trying to put together? So if you haven't really been paying attention or dealing with you know, how easy it is to follow, this is your time to start working on how easy this is to follow. You might want to put little guideposts, you know, like, what am I doing? Because like, I'm not looking to take off a point for every arithmetic mistake you've made here. Okay, if you screw something up, I'll take a point off. But if I see like overall, you have a direction, you know where you want to go, you know what you're doing with it. That one mistake is that's a 5 out of 6. You're fine. Okay. Sometimes it's not even that. Sometimes like, oops, screwed up something here. Okay. So now we have to figure out the d. We could have figured it out before. Fxx, Fyy minus Fxy squared at this point. Okay. Fortunately, though, we go back up here, we don't have any points to plug in. So it's just 4, 8, and 3 here. So we've got 4 times 8 minus 3 squared. Okay, so 4 times 8, that's 32, minus 3 squared, that's going to be 9. So what do we end up here? We end up with 23. Okay, so this is a positive number. Fxx, that was also a positive number. Okay, so we're going to go back to our text here. We have the discriminant is greater than 0. Okay, and we have Fxx is positive, so we have a relative minimum. Okay, so this means we have a relative min, and that's what we're going to give for our answer. My fingers are crossed, so I don't know. Okay, I'm just as likely, if not more likely, to find our local maximum minimum. Oh, no. There are numerical maxima. That's what I would say. I think I like a minimum, but it's not going to like this. It's going to tell me I'm wrong. Oh, no, it isn't. All right. Well, good. Have the courage of your convictions. Okay. There is a local minima located at, what did we say? -2, 1 or something? -2, 1. All right. There is a local minima located at 2, -1. And let's check it, fingers crossed. All right. Didn't like that. All right. Let's double check. All right. -2, 1. Okay. Let's see about that now. Okay. Again, like it's ridiculous to take off all the points if you mess that up. So that's not what we're doing. Okay. So yes, there's definitely partial credit involved with these things. Okay. Saddle, there's no saddle points. What are you doing? Give me a very easy question. All right. So let's see. Same question we pretty much did. Let's see if we can find another one. All right. But yeah, most of the problems that they hand you in this section pretty much look like these guys. These are all actually conic sections. Some of them are tilted. Okay. Because this little XY term, this means that they're tilted. A whole other class where you get to go and do that and figure out like, what is this? You get to draw like, you know, your ellipses and something like this. Okay. I don't know if it's an ellipse, but you know, that's the kind of thing that you're looking at. Okay. So we always know like, hey, there's a maximum somewhere here. Okay. So let's see here. We have, let's just do another one here. So f, x, y. By the way, these problems do take a little bit on the longer side. I always remember, this was Calc 3 for me. I remember we had our teacher, she'd always write down like, you know, here's your 20 problems for the night. And it was every other day class. It was Monday, Tuesday, Wednesday, Thursday kind of a class, or Monday, Tuesday, Thursday, Friday kind of a class. I always remember getting this section and she gave us like, you know, 6. We were like, Ms. Forrester, are you feeling okay? It doesn't seem to be the usual kind of amount of homework here. She's like, you'll see. Yeah, we'll see. Okay. So we have, oops, was that a cube? No, that was still squared. So let's see here, double check to make sure I got everything written down correctly. So we got -2x squared, -6xy, -5y squared. Oh, -14x, -20y, +8. All right, so let's see what we're going to get. Okay, so df dx, so first derivative with respect to x. So this is going to be -4x plus, I'm sorry, minus 6y. Okay, we're taking the derivative with respect to x, so this is all partial, so this is constant, we don't care. -14, that is 0, that is 0. So we're going to solve that for equal to 0. df dy, okay, so take partial with respect to y. 0, we have -6x. Okay, we have -10y, -10y. Right here, -10y. This one's 0, this one's -20. This is 0, and we're good. We're going to solve for 0 in a minute. All right, df squared dx squared. So we're going to take the second derivative with respect to x. So just this piece. So we just get -4. Okay, and then we have d squared f dx squared. We're going to go ahead and take this derivative. So 0, -10. Okay, and we're set. And then we have df squared dx dy. You can take them in either order you'd like. Let's go back up to here. Take the second derivative with respect to y. Okay, so remember to go back up to the first one. So this is going to be -6. If you swap them, right, take the first derivative with y, then x, we get -6 as well. So we're always going to have the same. It's okay. Okay, so, and again, at this point, you can calculate your d if you'd like to. Okay, that's going to be fxx fyy minus fxy squared, and we'll see what that is. Okay, so this is going to be what, -4 times -10 minus, and then we have -6 squared. Okay, be careful with your calculators. Okay, you know that a squared number is positive, but if you type in -6 squared, what the calculator is going to do is going to square the 6, order of operations, and then apply the negative because it's a multiplication. So you're going to end up with this. If you really want the calculator to tell you like what's going on, it's put in parentheses, then square it, and then you'll be fine. Okay, so just to remind us that that's the deal. Okay, because again, you know, I hate to be the bearer of bad news for you, but not too many people have passed calculus 2, and you might be insistent, like, I'm not the good one at math in my friend group. Like, well, in your work group, you're probably going to be the good one at math. Okay, so it's up to you to like be able to fix stuff like this. Okay, so there we go. So hey, my discriminant is 4, so it's positive. My fxx, that was negative. Okay, I could do this out of order because, like, no matter what my a and my b are, these don't change. Okay, these never change. So it's kind of like doing the second derivative test on a parabola. Like it's always going to be the same. The second derivative of x squared, it's going to be 1 or 2 rather. Okay. So we have that. So I'm going to go off and consult my chart. Okay, because that's what I have to do. So my value was, it looks like it was a saddle point, right? My d is going to be, well, the d was positive. Okay, so we're here still. Okay, but the fxx, that was less than 0, so we're going to have a relative maximum. Okay. So what about global maximums? Like we don't have functions that are going to do that. That was a lost section. That was 9.4 is when you had maximums, you had constraints. So you guys could do that, but they are more difficult problems. Okay, algebra-wise, they're more difficult. Okay, calculus-wise, they're the same. Okay, now we have to solve these questions. Okay, so what we're going to do is we're going to say we have 4x plus 6y, 4x minus 6y, and I'm just going to slide this 14 off to the other side, so it's going to be a positive 14. Okay, my other equation here, because we still have to know where it is, minus 6x minus 10y, minus 6x minus 10y is equal to, and what do we have here? We have equals 20. Okay, so one thing I'm going to do is I'm going to divide everybody by 2 before I get started. Okay, I might even divide by a -2. That way I can change all these negative signs into a positive, but you can't forget it on this side. So 2 over 2, that's going to be 2x. 6 over 2, that's going to be plus 3x. And then dividing by 2 is equal to minus 7. So notice I changed the signs here. Okay, let me double check, make sure that I've written that down correctly because I didn't. Okay, so that's going to be a 2x and a 3y. Okay, I changed the signs because I included a negative in here because I just wanted to make these positive, and I'll leave that one be negative. Same thing that goes here. So we're going to have 6 divided by 2 is going to be 3x. Okay, 10 divided by 2 is going to be plus 5y, and then we'll have a negative 10 over on this side. So I swap the signs, leaving this side, right side to be negative, left side to be positive. All right. So, and again, we have to figure out like, well, do you want to do elimination? Do you want to do substitution? This is your choice. Okay. So what I'm going to do is I'm going to multiply by 3. I'm going to multiply that by 2. Let's go ahead and say we're going to multiply this one by a -3. And this one is going to be a +2. Okay. 2 times 3 will be 6. 3 times 2 is going to be 6. So you're free to choose to do this to y too. Okay. It really doesn't matter which one you've chosen. Okay. Since 2 and 3 are smaller than 3 and 5, I just picked the smaller one. But that was my choice. You can make a different choice. Right? It's entirely up to you. So when I multiply that, that's going to be minus 6x, okay, minus 9y equals positive 21, right? And then here we're going to have 2 times 3 is 6x. 2 times 5 is going to be 10y, right? And this is going to be negative 20. And all I'm going to do is add these together. See, I have to make sure I'm picking them out of this textbook because these are nice. Okay, if I pick them and make them up, they are terrible. So I try to be nice and at least grab something that's similar to one of your problems so that the algebra actually comes out to be kind of nice. 10 minus 9 is 1, so we just get y, and then 21 and negative 20 is 1. Oh, okay, y equals 1. I'm not going to argue. Okay, go back to any of the equations you've had up until now. So either of these, anything you'd like. I'm going to pick 2x plus 3y is equal to negative 7. 2x plus 3y is equal to minus 7. Okay, 2x plus 3y equals minus 7. Just going to plug in my y equals 1 here. So we have 2x plus 3 times 1 equals minus 7. So that's just going to be 3. Right? So I'm just going to subtract 3 from both sides. So we end up with 2x equals, remember we're adding, okay, 3 and 7 will be 10. So x will be minus 5. Okay, so our point minus 5 and 1. Okay, now I'm ready to answer the questions. Okay, again, I know I did the D part, the discriminant part out of order, but there wasn't an A and a B to plug in, so we don't have to worry about that. You could do them out of order in that case. Okay, what do we find? That this was a relative max? Okay, fingers crossed. Okay, yeah. All right, there is a local maximum listed at minus 5, 1. Okay, so here we go, holding my breath, check the answer. Yay. That was the only critical point we found. There are no other minimums. There aren't any other saddle points. The way that's going to happen, okay, so you might look, they all seem to be the same. Like they kind of are, because we want to give you equations that are relatively easy to get. Okay, so that's what's going on here. So if, check for the worksheet, there is an x cubed or a y cubed problem, or God forbid, like a square root of x, okay, or an e to the x, something like that, you are going to get more than one critical point, okay, because there are going to be x's in here, and you're going to have, well, you're going to have x's left over in these equations, okay. They're going to be nonlinear equations you have to solve, substitution, always substitution with those, but those are the kinds of things you have to worry about. So if everything is what they call quadratic, okay, you have an ax squared plus a bxy plus a cy squared dx plus ey plus some kind of a constant. Those are all the kinds of questions we've done so far. These are the safe ones. These are nice and easy ones. Okay, I might throw in one that's got like you know, an ax cubed, something like that. Okay, but I've got to be careful about picking it. All right, and again, check worksheet. Put one there, like that in there. Okay, show that this has a relative minimum, even though the derivative in the theorem is 0, but not the derivative, the discriminant in the theorem is 0. So, like, okay, that's fine. Okay, so let's see what we have for critical points. All right. So we have what? 1 minus x to the 4th. So you can kind of tell by just by the geometry of this thing, right? X to the 4th kind of looks like x squared, so it's a parabola, but facing down because it's negative. Y to the 4th is also a parabola, so it's again a parabola but facing down. Okay, so what this thing is going to look like is pretty much like a cup that's down. Okay, so that's kind of what we're looking at. So we could tell, like, hey, there's a maximum here, relative max. Okay. So, but we'll go through it the long way here. So we'll say, okay, well, partial of x, right? We have 4x cubed negative. Partial of y, 0, 0, minus 4y cubed. Okay. And this has got to be our critical points. Okay, so we're going to say, well, negative 4x cubed equals 0, negative 4y cubed equals 0. We have to solve for x and y. So that's going to be x cubed equals 0, y cubed equals 0, x is equal to 0, y is equal to 0. Okay, we can just take cube roots on both sides. So the critical points are going to be 0, 0. Okay, so that's not too bad, right? So we'll go through and do that. Oops. Actually, I think it's going to be 1 or something. Let's check. Okay, so we're okay. The value of the function at the point, that's what I'm looking for. So I plug in 0 and 0, we get 1. Okay. I really wanted to ask this one, but I thought it was too easy. Okay. I mean, it's a nice question because it does kind of guide you through the geometry of what's going on and ask you if, you know, like, can you tell from the graph what's happening? But it's also, because it's also a really complicated topic, you have to make the problem pretty simple to do it. So I thought this one was too easy for a test question. Okay. So yeah. So the value, okay. So how do I know this is a relative maximum? The value of 1 minus x to the 4th y to the 4th must be less than 1 for anything you're going to pick. 4th powers are positive, 1 minus a positive number. One's going to be, you know, the best you're going to get is 1 minus 0. Minus 0 is 1. Anything else is going to be a little bit bigger than that. So 1 minus bigger than 0 is going to be a smaller number than 1. Okay. So we don't care about the derivative of xx being negative, okay, because that doesn't tell us as much as we want to know. We never cared about the derivative of yy, okay? And we know that if we start plugging numbers in here, 1 minus stuff is going to be smaller than 1, okay? So that's what we're going to go with, okay? Yeah. So again, you know, application problem, but we are still x squared, y squared. So it's the same kind of problem that we did before. I think I picked this one before too. Okay. And again, we're only dealing with x squareds and y squared. So it's the same type of problem that we did before. I may do another video to demonstrate some of these too. Okay. But that is effectively your 9.3 kind of homework that you're working with. So we'll do that, and I will go ahead and stop recording. Okay.